Okay, welcome to this technical workshop on CCS. This is Gunnar speaking. I will just basically introduce our presenters today and perhaps lead some of the discussion that we may have in between. We have a general topic today based on the CCS reference architecture or communication framework and how it may map to popular cloud platforms. And there will also be a general discussion about how to apply and choose cloud platforms from the popular vendors that are out there. So why don't we start right away with Iyyaz presenting on introduction of platform as a service, some about IBM Cloud and various topics. I'll hand over the sharing to you, Iyyaz.
Okay, thank you. Sorry, I'm just looking for the share option on this. Okay, good day everyone, and I hope you're all well. So my name is Iyyaz.
You may want to switch your displays. We're seeing the
you're seeing the wrong
speaker
one.
notes now. If you go to display settings, just swap those.
Okay, is that better?
It's not yet updated on my screen, but still seeing the.
Okay.
Let's try again, maybe.
I'll share content and then share a different screen.
Yeah, that looks better.
Okay, great stuff. So thank you very much. Yep. So my name is Iyyaz. I work for a company called CobraSphere, and I'm going to talk to you about platform as a service vendors and what we've been doing as a team in terms of mapping the CCS framework on these various platforms. And in today's agenda, when I switch the slide, I'm going to be talking about an introduction to the different cloud vendor environments, the different deployment paradigms for the CCS framework, security measures in cloud environments, and CCS mapping and what we've been doing as a team, a production concept in IBM Cloud, and managing cloud infrastructure. And there'll be some time at the end for any questions, but do feel free to ask me during the call today. So in terms of an introduction to the cloud environments, there are three typical architectures across various different cloud platforms. And the first one that you may all be familiar with is a single cloud environment where a customer would use a single cloud provider to serve all of their applications and services. These environments can use both private and public clouds. And this is typically appropriate for organizations that are starting out with the cloud, without becoming overwhelmed with all the different services offered. The second one is hybrid cloud environment, which uses a single cloud. Oh, sorry, something's gone wrong with my laptop. Can you hear me, guys?
Yes. Yeah, we can hear you.
Yes, you can hear me.
Fine,
okay,
yeah.
Great. So the second one is the hybrid cloud environment, where an organization would typically use a single cloud provider and they may use their on-site infrastructure. This is typically the case when a customer has already built a plethora of services in their local data center inside their office. And the third one is the multi-cloud environment using multiple cloud vendors, and that allows the customer to utilize specific features available to certain vendors. and also it allows prevention of lock-in and dependency. So it puts the vehicle OEM or the customer in more control. In terms of multi-clouds, they can be connected at the network level, either with a VPN, with a VPN to make all the services visible with private endpoints only, or at the application level using externally visible application endpoints. Okay, and the next slide. So in terms of our team's take is that the multi-cloud is the best suited architecture for vehicle OEMs. Obviously, you get the high availability with a global positioning of all the different cloud vendors. There are also access to specific compute or data services such as analytics or IBM Watson or anything specific to certain key vendors. There's no vendor lock-in, and also it gives the vehicle OEM the ability to scale on demand, either with predictable demand or unpredictable compute demand. So that's our recommendation as a team. And in terms of the paradigms for CCS framework, there were three that we looked at, and they are virtualization, containerization, and the serverless architecture. And the key benefit with virtualization is that it's, of course, fully customizable. You can pretty much do whatever you want with it. You can bring your custom images from what you've done before. I think everyone knows that. With containerization, it's a build once, run anywhere paradigm. And when you're building these Docker containers, you are locking in all the dependencies. With the serverless architecture, you're simply pushing the code to production and all the dependencies are acquired at the time of provisioning. Now, this may not be suitable for all use cases because, in some environments, I've actually seen where some people might prefer to lock in all of their dependencies in that binary blob of a container image. But then, of course, you've got other benefits with serverless. So when we're looking at horizontal scaling, the effort for that, particularly when you want to scale your cloud resources across multiple vendors, with virtualization, the effort required might be considered quite high compared with the others because you obviously have a custom virtual machine. You may need to create images for that and then deploy that across the other cloud vendors. With containerization, the effort is relatively low as long as the other cloud providers support Docker Engine, which most of them do now. And all you simply need to do is to instantiate your Docker containers in those other platforms, and away you go. With serverless architecture, you may need to make some tweaks to your manifest YAML or other similar files, other configuration for that particular platform as a service vendor. So there might be some effort involved in that one. When it comes to vertical scaling, when you want to scale your resources within the same platform, again with virtualization, it depends on the vendor. They may impose limitations on how far you can scale your virtual CPU, your virtual RAM, and any other storage attached to the VM. When it comes to containerization, you have got the Kubernetes or Swarm or any other kind of Swarm cluster, which allows you to, it doesn't scale the actual container, it just spawns additional ones. So they will just scale based on your parameters configured in Kubernetes or Swarm. When it comes to serverless, it's all handled by the platform as a service vendor. So depending on how you've configured the limitations and the scope, if there's a sudden demand, your serverless environment will automatically scale. Okay. I'll stop there in case anyone has any questions. Okay, no. So in terms of cost, when it comes to virtual machines, you are essentially paying if you're paying monthly, you're paying for the 720 more or less hours uptime every month, regardless of the demand. And with containerization, there is a minimum cost for having two of your nodes running, plus a load balancer and possibly a firewall. When it comes to serverless, you're only paying for the compute cycles, and you actually pay nothing when the compute cycle is inactive. So that there are, so if you're obviously if you're scaling for around the clock services for different parts of the world, you will only pay for what's needed at when those vehicles are active. And when it comes to DevOps, for virtualization, that will obviously depend on the build, but assuming you have SSH and everything configured, you can use GitHub Actions, Bitbucket pipelines, Ansible, or any of the other ones. When it comes to containerization, you can also use GitHub Actions, Bitbucket pipelines, or even the platform's native tool chains to build your Docker images, push your Docker images to something like Docker Hub, and then when it comes time to deploy, those Docker images are pulled into the Kubernetes or Swarm clusters, and they are instantiated. The containers are instantiated. Any database migrations can be done, and the system can continue to scale as needed. And when it comes to the serverless architecture, your GitHub Actions or Bitbucket pipelines or any other system that you may use, uh, they will continue to push either push to the serverless architecture, or you can actually have the PaaS native tool chains pull the latest commits based on certain triggers, and it will fetch the code base, deploy it to the serverless node, and then it will scale as needed. So that's kind of a snapshot of the three different paradigms for the CCS framework. And as far as I'm aware, we've done the containerization and serverless examples in our recent case studies. So before I move forward, I'll stop there in case anyone would like to ask any questions.
Well, Manu here, hello. So I'm
Hi.
Manu Kemppainen from Bitium. This is our first time in GENIVI, all meetings, so we joined it on January. And I put to the chat a question about the storage leveling compared to this. I understand that the Dockerizing is good for the execution, but the actual data lake or whatever storage is used, that's typically not included to the Docker itself. It's not containerized. So if you have the multiple vendor, have you already considered the strategy how to split the data?
Yes, that's a very good question. So welcome to the group, Manu. First of all, so yes, you're right. So the Docker containers are not supposed to store any data. They are immutable. So what normally happens is you have an object storage on either one of the cloud platforms or multiple ones. You've got the database, and you've got database, and you have the object storage to store any files or data or any content. So yes, all of that should be outside of the Docker containers.
Yes, have you considered that is it going to be so that the Docker itself is kind of if it is a serving Docker, that it is serving with only like one database, and then there are agents that are distributing the data to other vendors if it is a multi-vendor, or is it all going to be in one Docker?
Yeah, I see what you mean. So
yeah, it's kind of a
yeah,
microservice approach.
exactly. Yes. Yeah, so I do have a slide on this very topic, in
Okay,
fact.
okay. I'll wait to that one then.
No, that's fine. What I can tell you is that yes, I mean you're on the right lines. What we should have is separation of concerns. That's the topic I'm going to talk about, and it will allow for one particular microservice which is only involved. Its only responsibility is to handle data and pass it to other consumer services, if you like.
Yeah.
And I can, if you like, I can talk more about that when I get to that slide and see if I've answered your question. Would that be okay?
Okay, that's fine. That's good.
Okay, brilliant. Thank you. Any other questions in the meantime? Okay, no worries. Okay, in terms of security measures in the cloud environments, of course, when you start to deploy things outside of your office premises, or wherever, once you start to deploy in the cloud, yes, you must think of security. And these are the two areas that yes, there are many security options available, but the key ones that I'd like to discuss today are endpoint protection and identity and access management. So with endpoint protection, every time you've got public endpoints, it's always worth, first of all, encrypting the connection with TLS, which was known as SSL before, and also to hide your endpoints behind a proxy. So you could use something reverse proxying using something like Cloudflare, which also provides the threat detection and prevention. And what that does is it will prevent things like denial of service attacks if someone or a bad actor is trying to carry out some malicious activity on your endpoint. The reverse proxying will detect that and block them immediately. So, and of course, these endpoint protection settings can be configured to different levels. They can be restricted and tied into identity and access management as well if needed. So you've got that option as well. So when it comes to identity and access management, this in the use case for CCS, I'm thinking of system to system access and user access. And of course, IAM solutions, they are responsible for authentication, verifying a user or system identity, first of all, and then authorization. So making sure that the actor that is trying to access the system is only able to access the areas that it has been permitted to. So the whole idea of the IAM solution is to make sure that actors, whether they are in a certain group, they either have group level access to certain data or certain endpoints, and nothing beyond. That's the whole idea behind it. And there are two providers that pop up quite frequently in different circles. One of them is Okta, and the other one is Auth0. Okay. And in terms of CS mapping and what we have done as a project team, we have first of all we've gone through a round of selecting the providers, and you can see the four major players in the diagram on the right. So these are the big name vendors that already have some level of investment in automotive use cases, and some of them have gone to certain lengths to provide additional resources to support obviously the automotive use cases, but also they have the deployment paradigms that I've discussed in earlier slides, as well as of course their DevOps operations. And what we were thinking of doing next was to address, as a team, we're looking to, as you were saying, Manu, we're looking to go for this separation of concerns. One of the things me and my team want to do is to separate some of the code base into microservices and introduce more levels of abstraction, so that we're moving away from this model where we have a code base which contains more than one service, and then these two satellite services accessing the same database. We want to move to a model that looks more like this. So you have the API, you have a microservice that exposes an API, and its job is to talk to its own database. And if you need another access to another database, you talk to that database via the API. And then you've got functions as a service, cloud functions, to perform some non-database related activities like calculating something, or I'm thinking of the vehicle, the VSS, the vehicle signal specification, which does generate some files. So those kind of things could fall into functions as a service. Now, one of the reasons why we're keen on this model is introducing the level of abstraction gives more flexibility to allow the OEM to decide, to have kind of a decision-making power on what databases they might want to use. Some may say, we've stuck with Oracle, we've stuck with MySQL, and we want to use MySQL. Others will say we want to stay open source and go with Postgres, in which case all of the entity specifications are in these microservices, and they will handle all the necessary calls between the consumer and itself, and then they will talk to the abstraction layer, which then talks to the database. So it kind of opens up all of those possibilities. And also as and when more people join the GENIVI team, the CCS project, we can start dividing most of these microservices between teams. So the separation of concerns and focus will kind of address all of that. So Manu, does that address your
Yes,
question?
yes, absolutely.
Yeah.
Perfectly in a question, because what we are kind of aiming to is having a really small microservices, because then those microservices on edge, they can be moved to the edge computing. In a case when there are a lot of data coming, for example, from the vehicle, but not all that data is needed as a protocol in the cloud itself. So there could be an edge computing unit that is combining those data to the larger batches to the cloud.
Exactly that. And also, these microservices would scale independently. So,
Yes.
for example, if this API is quite busy, this can scale vertically, or if it needs to scale horizontally, that's also possible. You know, and of course, the vehicle OEMs will want to watch on cost as well at some point. So, they will have an accurate measure of which endpoints are busy, which microservices need more scaling, which need more optimization. It's kind of a more future-proof solution. Okay, does anyone? Okay, I think Gunnar, you wanted to say something?
I just made a brief note that you mentioned Postgres and MySQL, and of course we've been discussing time series optimized databases for some of these cases where you collect data that is clearly time series oriented, because those are optimized for that purpose.
Okay, yep. Thank you for that. Any other questions before I move on? Okay, I'll move on to the next. So this is a production concept that we've come up with specifically for IBM Cloud based on our knowledge of IBM Cloud. And starting from the left, we've got the third-party services. They could be the partners or particular users in partner companies, whichever. They are connected to the internet, but they will hit the proxy first, obviously. I mean, they won't know that, but their connections would come through the proxy, be identified, authorized as needed, and then they will have access to the data service API, which we have modeled on IBM's Cloud Foundry. And that server API is then connected to the OVDS server, which has access here to this object storage. This would contain some of the JSON files and anything that was generated by the VSS or other components. OVDS server is also a Cloud Foundry instance, and so is the OVDS client, which then connects obviously to the proxy as well for the vehicle. So all the vehicle operations would go through the proxy, be identified as well, and the client would interact with the vehicle that way. And in this particular diagram, we've modeled the database. This does say Postgres, but yes, it can be any database. It could be the time series ones as well. And you can see here, these two are connected directly. But what we envisage is that this link here would not exist, and the OVDS client would talk to the OVDS server, which would have all of its entity mappings with the database. So, for example, if the team was to manage, if there was one team just managing the OVDS client for various reasons, then it would be their responsibility to make sure that the specification of the entities are in sync with everyone else, but also just to expose all of the database interactions as endpoints for the OVDS client. That's how we envisage it. And we've also got the live simulator here. If you are simulating the architecture, you would need the live simulator, which is connected to the OVDS server. Okay, so that's the production concept. Any questions on that? Okay.
The live
Yes.
simulator here is not a digital twin. It's kind of simulating the OVDS more than.
It's simulating the vehicle signals.
Yeah, but it's kind of providing the signals, or is it
yes.
using? Yeah. So it's not a digital twin. Okay.
Yeah, I don't. You know, I'm not 100% sure if it's the digital twin. Gunnar, is that, would that be the case, that the live simulator?
I can explain what it is. In the interest of time, if we want to keep the time, we should wrap up in a few minutes and continue in the agenda. I don't want to get into defining digital twin now. I think that will be a fairly long discussion. But the simulator that has been produced so far, it basically takes data in the format that is in the OVDS server, which is where we collect real-world data. So it essentially will be able to take collected data from a real vehicle and feed it back into the system as if it was a new vehicle.
Yeah. Okay.
Right. So it acts in real time exactly like a vehicle acts. The signals are coming in that same sort of pace as they were recorded originally.
Yeah, it's kind of works opposite to the digital twin. Okay.
Yeah. Yep. Right.
Okay, great. I do realize I'm over time, so I will try to move forward very quickly. I'll move to the next slide. So when you're thinking about your cloud infrastructure, and in particular for vehicle OEMs or any large enterprise, you would wonder, how would you manage such a vast and complex infrastructure, not only in one cloud provider, but in many? So there is a solution for that, and that's called using infrastructure as code, where you would declare all of your cloud resources across multiple platform as a service and also infrastructure as a service vendors. And it would all be specified in code, which looks like the examples on the right. I'll briefly talk about these examples shortly. So one of the frameworks that we use is Terraform, which is by HashiCorp, and this has an ever-growing library of provider modules which need to be added when you need to access various PaaS or IaaS providers. You also have other ones from the PaaS vendors or things like Ansible. With PaaS vendors, you've got something called Google Deployment Manager, which works specifically for Google. Other providers may have their own ones and also their own SDKs or CLI interfaces as well. But we like to use Terraform just because it's workable for a broad range of providers. And when you look at the benefits, if I was to summarize the benefits, you have disaster recovery. So if in the unlikely event something happens to your infrastructure in the platform vendor's environment, you can quickly redeploy by applying your infrastructure by just rerunning or reapplying the code, which will set everything up as it was before. In addition, when you need to scale your infrastructure or make any changes, it's minimum effort for the developer. All they need to do is to make tweaks, adjust limitations. For example, if they need to increase the memory across a number of database servers, they could change these numbers, rerun the code, and that could effectively upgrade all of the databases across different vendors. So it's ease of management, and also this particular well, the infrastructure as code also becomes your specification for your infrastructure. Okay, so in the interest of time, I'll just quickly wrap up the last one. So I think the next steps are to, as I said, address the separation of concerns. And what we'd like to do is to repurpose the proof of concept code base into production grade cloud services by splitting the CCS projects as single service modules. And where possible, we'll introduce functions as a service and then decouple the cloud resources from the vehicle specific databases, and also replace some of the hard coded configuration with runtime environment variables. And that will address some of the things where you have Docker containers that you instantiate, but they are used for different purposes, different environments, test environments or production environments. That's just a short list of ideas that I wanted to talk about today. So I'll wrap it up there. It's 29 minutes. If anyone has any questions, it's all yours.
Okay, if
Yep.
there are no more questions, I suggest we move on in the agenda. Next up, I will play a pre-recorded presentation by Kevin Valdek of High Mobility. And we may have some time to discuss that after. So 1 second here. We get the audio.
Hi, I'm Kevin Valdek. I'm the CTO of High Mobility, and of course also part of the Cloud and Connected Services project team. In this session, I will go a bit more deeper into AWS. So of course, Amazon's platform has been one of our targets that we've been looking at for the framework mapping. And in this specific session, then looking at how Amazon Web Services, what type of solutions they're offering here, and where we see a good fit of what services to use for our components. The AWS automotive solution is nothing new, really. They have been AWS has been promoting it for quite some time. And there is different blog posts, how they describe the different services that can be used. There's just a diagram from one of them where they show a range of different native services that they have that can be used in an automotive cloud solution. And we have also seen that there are a lot of OEMs who have adopted AWS for different purposes, and several brands have announced partnerships, both strategic and also really operational already for many vehicles. So can be a good fit to use it, of course. The reference solution that AWS has been provided here to the right uses different components. We have been looking at that as a bit of an inspiration, but not only, but going beyond those services, because AWS really has hundreds of services that can be used to really identify what fits best into our specific framework. So if we apply AWS to our framework, or to the Cloud and Connect Services framework, or the other way around, then we have identified some kind of key services that can be used, and also alternatives. So if you go from the bottom of the screen, we have AWS IoT. So AWS IoT is a broad framework with a lot of different components that is used to manage different devices or edge devices that are connected to the cloud. And of course, in our case, the edge device is the vehicle. So there are both service or software that runs in the vehicle that connects to the cloud, and also services on the cloud side that manages all of these different vehicles that are connected to it. There's also something called AWS Greengrass Cloud Service, which is an extension of AWS IoT. In some ways, it's a complementary software kit that adds additional features, and I will speak about those shortly. Then we have AWS Kinesis Firehose, which is more or less like a data sink that can manage a lot of vehicles. Of course, if you don't just have 1-2 vehicles that are connected, it's typically not an issue to handle it. But if we consider millions of vehicles that are connected, then some kind of scalability has to be on place, and the Firehose takes care of that. I've also marked AWS Lambda as one of the components to manage the kind of interface between the cloud and the vehicles. Lambda is providing more or less like serverless functions that can be executed when needed. It can be used more or less like some type of glue between the different applications. As for the database, there are a lot of different options in AWS. Simplest one is RDS, or Relational Database Service. It's basically an instance that can run any of the popular AWS or any of the popular relational databases like Postgres. We have AWS DynamoDB, which is a key object value store, and also AWS TimeStream, which is really for time series storage. So all these can be used together or separately. It really depends on use case. We'll speak about the feasibility in the next minutes. So as the data can be stored, the third part, or the third main component, is the exposure of the data to third party and to mobility services. A lot of different options here. Simplest one is AWS Lambda, again, a serverless approach where any type of functions can be written. In our case, it's a straightforward implementation of a REST API or a GraphQL API that can be done. We got AWS Kinesis data stream, so you can see that's also in the Kinesis family of the Firehose that pulls in the data. We can have the data streams service to expose the data as a live stream to third-party services, so that can cater for some other use cases than, for instance, AWS Lambda, which perhaps is more transactional. And then we got the AWS Simple Queue service that we also see can be a good fit. It's a queue, so it's not directly a stream, but it's also built to manage large amount of data, meaning that as data is being gathered in the databases, it can be pushed onto the queue, and then the third-party services can all the time look, is there anything new in the queue, fetch that data, and start using it. So these are the main services that we have been looking at, and that can really be feasible for implementing a complete cloud solution to work with the connect or the data, VSS data coming from the vehicle. Now, a bit more into specifics. So AWS IoT, it's not only something that runs in the cloud, it's both for, in our framework, the data server and the data client. So that means that for AWS IoT to really work, yes, you have a service running in the AWS cloud, but it also expects that the edge devices are compatible. And compatible means that it adheres to the protocol that AWS is expecting, or essentially that it runs the SDKs or software within the edge to manage the data. So it is a difference from the POC that we have done. So we have been using, for instance, this or W3C VISS specification or a protocol to transfer the data. We also have the client and server implementations for the AWS scenario. If using the AWS native service, that would mean that also the vehicle has to have software for running and managing the connectivity from AWS. This IoT SDK from AWS supports typical publish subscribe methodology. It can use HTTP, WebSocket, MQTT out of the box. In addition, it has some different services for analytics and monitoring on the cloud side. So all that, when it comes to connectivity, basically the IoT services manage it. Then the next line here is the AWS Greengrass. As mentioned, it's a bit like an extension or complement to AWS IoT. It provides additional features like over-the-air updates and also some kind of Lambda function execution. That's really a question if it's needed, but what it allows is that you can have some functions that either run in the cloud or in the vehicle, depending on implementation, and you can reuse that code. So there are some benefits. It also has some more advanced things to kind of capture data or to have data instructions or data job instructions that can be configured on the cloud side and synchronized to the vehicles for instance, that, okay, during this period of time, now this specific data should be captured, which can really be beneficial if you consider that the vehicle is generating so much data. And in this scenario, you can have specific jobs that focus on specific data sets based on the use cases that are currently being implemented or the services that are being used by the driver. Firehose is a data sync. One thing that it kind of provides is a way of processing data. So in the case, if the raw data coming from the vehicles have to be processed before stored in a database, it can be a convenient option to use if any sort of rules should be built into it. AWS RDS, the last line on this slide, is of course the relational database. In the POC that we implemented, we used SQLite, which is a relational database, of course. So a continuation from the POC would be RDS instance up and running using basically the same schema as we had in the POC. To follow on the next components, we got AWS DynamoDB, key value database store, which sometimes is being considered as a good fit for data lake implementations with a lot of data. We haven't looked too much into the implementation specifics of the benefits of using a key value store yet, but at least that's one service that could be used for that. Second row is AWS TimeStream. So this is something we did look quite a lot into in the early phases of the project, as we were already considering that, of course, having the server or the data client, so the cloud, connecting to the vehicle and just fetching single data points might not be the scalable approach in the long run, but it is about having time series of data that is captured in the vehicle and then transferred to the cloud. And we also even designed first kind of spec or inspiration for a specification in this project, where we considered, okay, this is the time series, it captures different data sets, different samples. It could be the same data point like the speed of the vehicle, or it could be a mixed data set with the speed, the location, and the mileage, and so on. So the time stream database could be a good option for it. A big difference for AWS TimeStream compared to something like RDS relational database is that RDS is one instance. Of course, you can have several instances, you can have replication and scalability, but TimeStream is a serverless database. Basically, you don't have any control of the specific instance. AWS manages all of it. You just have an interface to store time series data. Then the last three components, which is about the exposure to third-party services. AWS Lambda, as mentioned, good approach for REST APIs or GraphQL APIs. In the POC, we had a GraphQL API that was exposed. This can easily be ported to an AWS Lambda application. Basically, the difference would be that it's a configuration of making the GraphQL server serverless, so to speak. And there are existing schemas to handle that. AWS Kinesis Data Stream for more streaming use cases, can be for more advanced mobility use cases, for capturing live stream data when the vehicle is being driven, even to do profiling or managing the understanding how the vehicle is being driven, but also for perhaps anonymized use cases where data is being streamed and also pre-processed and anonymized, can be used for different services. So it really depends on the use case, what type of interface is best, but both AWS Lambda and data streams can be quite complementary. And then Simple Queue service. One thing to mention about Simple Queue service is that it can be combined with Simple Notification service. So with SQS, you basically always, as a data client, you always have to ask for, is there any data available? But with SNS, the notification service, you can also have push messages that, okay, there's new data available. So it's easy for the data client to know, okay, now I should fetch new data. Can be especially useful for vehicles, as they're not always driven. So as soon as the vehicle starts to generate new data, there could be a notification system going on, and the SQS is then, the queue is filled up with data that can be fetched by the data client. So these are all the different options, and we are not focusing on any specific implementation at this point of time. And of course, we're also not saying that all these services have to be used for the communication framework. It really can be that, for instance, maybe the database is a good fit to be used, but maybe the AWS IoT framework, which spans into the vehicle and needs a specific vehicle implementation, is too much to do or doesn't add any real benefits. And of course, then it could be that just the database components and the third-party interface components are used. So at least there are a lot of good services that can be utilized from AWS to do an implementation. As in some final remarks, so some options for the POC that we did and how it could be mapped to AWS. So of course, a simple approach or a different approach from what has been presented here is to really just deploy the containers that we have in the demonstration into computing instances. But as you can understand here, in this approach is more about using native services from AWS. So some of the options we show here that are kind of could be interesting next steps for the POCs, that the vehicle client, which is running in the cloud, would be written in AWS Lambda. So making a serverless application, and we would still use the W3C VISS vehicle client that was implemented in the POC. Of course, it was implemented as a Go application, and this could then be modified to run serverless, so to speak, as Lambda functions. The second thing that could be implemented is that the VSS database that we had right now in SQLite could be switched to AWS TimeStream. So this would be interesting to see about the performance and also scalability, as we know that essentially the data coming from the vehicle is a time stream or a time series of data. So using it, AWS TimeStream could be interesting. Of course, it also means that the vehicle client has to implement the interface to AWS TimeStream instead of the existing, using the existing queries of the SQL database. And lastly, for the data API towards the third parties, also AWS Lambda can be used. As we have the GraphQL server, it can be converted to a serverless application with reasonable effort and run as AWS functions essentially. So we would have a complete loop running in the cloud in AWS, two AWS Lambda services, so to speak, on both ends, one on the vehicle end, one on the third-party end, and in the middle having the AWS TimeStream database. So that's some of the kind of first findings or the mapping that we have done for AWS. And of course, if you have any questions, we are happy to, other colleagues from the CCS team, of course, happy to answer any questions. So with that, thank you for listening, and I hope you found it interesting.
Okay, thank you to Kevin Valdek for that presentation. We had planned to end this session at 1:15, but we got started a little bit late, so 5 minutes more would be perfectly fine. What's your feeling, Nate and Kevin? Would you like to get started as soon as possible, or shall we take a little time for Q&A?
Maybe we can see if the audience have any questions right now.
Yeah. So you have 20 to 25 minutes left of the session in total.
Sounds good.
We can always return to questions at the end if we have some extra time, and we also have additional workshops later this week. And obviously, as I always point out, the primary work is done in the weekly projects that are active all the time, every week. So if this is only getting people interested, then you can participate in the deeper discussions on the ongoing projects every week and not only on the all-member meeting. Okay, I would propose that we turn over to you, Nate and Kevin, and you will be presenting similar topics with a focus on Google Cloud, I believe.
That's correct. Let me just share my screen. Let me know if you can see
Yeah,
it.
it looks
Okay.
good in full screen. Yep.
Perfect. Okay. Good morning, everyone. I hope everyone's doing well and have been enjoying the contents of the all members meeting so far. I'd like to welcome everybody to the third section of the CCS technical workshop, and offer a big thanks to Kevin and Iyyaz for walking through the AWS and IBM Clouds respectively. Nate and I are here today to talk about the communication framework for the CCS vehicle model to Google Cloud. But before we begin, I'd like to offer up a quick introduction. I'm Kevin Sousa. I'm part of the solution engineering team with GeoTab. My focus has been on hardware and embedded integrations, as well as strategic OEM partnerships. Nate, if you don't mind saying a few words about yourself before we begin.
Sure, thanks, Kevin. This is Nate, and I'm the senior manager of data platform team in GeoTab. My team is focusing on building the data platform team, and at the same time ingest all the data into our data warehouse and do the consuming services for the AI modeling.
Thanks, Nate. Now, giving a bit of an outline before we jump into the content. So what you can expect for the flow would be a brief introduction of who GeoTab is and what we do, as well as an overview of the Google Cloud services. Then we walk into how GeoTab uses the Google Cloud, power its backend, and we'll talk a little bit about the mapping of the cloud and connected services architecture to Google Cloud services, and then Nate will walk through the overview and key features of each of the Google Cloud services that we've outlined. But to start us off, who is GeoTab? We're a world leader in connected vehicle with over 44,000 customers and 2.3 million active vehicle subscriptions worldwide. And what that equates to is something over 500 or 50 billion data points collected off of our connected vehicles subscriptions daily. Nate, do you mind giving an overview?
Yeah, sure. So for GeoTab is fully built on Google Cloud platform, and if we catalog all the services that Google Cloud provides, it could go to those 10 catalogs. And GeoTab is actively using all 10 catalogs, but I'm not going to cover all of them. So for this presentation, I'm going to cover the computing, the storage database, something related to big data, Internet of Things, and Cloud AI. Yeah, can I go to next slides? So this is a very simplified architecture of how GeoTab is collecting data with Google Cloud platform. We have 2.something million active vehicles connected to GeoTab platform, and all the devices are sending their data periodically to our gateways, which is built on top of cloud compute engine. And then the data were archived in some small batches and was sent to Sorry, I have to unmute some alarm.
Did we lose you, Nate?
Oh, sorry.
Your microphone is a little boomy. I thought maybe you were trying to adjust the sound, but
Yeah, got it. Am I back?
yeah.
Sure. Sorry about that. So, was wondering where I was lost while I'm talking about the. Maybe I can start from this slide. So, as we were mentioning, Geotab has 2.3 million active connections from all the chunks to our Geotab platform, and all data were periodically sent to the gateway servers built on top of compute engine, and then data was archived to cloud storage as microbatch files. Then we have our data platform built on top of Kubernetes clusters, reading data from cloud storage and archiving it into the second tier of storage to keep our cost low. At the same time, do some streaming analytics and ingest data into BigQuery and forward them to the other Kubernetes-based cluster to serve the model. Yeah, that's the brief overview of how Geotab is ingesting data and also consuming data, persisting data into BigQueries. I will talk about the services that I mentioned in this architecture in detail later. Yeah, Kevin, we can go to the next one.
Yeah, so on this slide, wanted to highlight kind of a basic IoT flow, and this is a sample architecture that is shared by Google on their cloud platform, their cloud platform website. But kind of bringing this back into the CCS CCS vehicle architecture, and pardon, I'm going to read a little bit here to make sure that I'm not misspeaking as I talk. But the IoT core would make a good candidate for CCS components such as the data server and the data client. It also would work well for in-vehicle components. The cloud IoT is an equivalent to AWS IoT and IBM's IoT platform, and fits the application of the cloud data client. PubSub, Dataflow, and Dataproc are services that can run VSS through and the OVDS server. InfluxDB on Google Cloud, BigQuery and Cloud SQL can power the OVDS database. Cloud Functions, App Engine, and Bigtable can host the GraphQL database, also power REST APIs, and offer up any third-party interfaces. AI Stream Analytics, and Dataflow would also be good candidates for cases that require high-rate data streams, and also functions that have yet to be captured in the CCS model. Nate,
Yeah, sure.
Can you now provide the overviews of the different functions?
Yeah, sure. Jumping into different catalogs of services that Google provides. The first one is IoT. The IoT core is a fully managed service to easily and securely connect, manage, and ingest data from global devices. And it has a lot of features like device manager, protocol bridge, end-to-end security, stuff like that. Geotab is currently not using cloud IoT in our production environment. We're still doing research in this. This is a relatively new released service from Google, but we are actively doing some research and do have a plan to roll it out in our production environment. Yeah, After this, I think I would like to jump to the compute services that we get from Google. Kind of, if we can, yeah, next one. So Google has quite a lot of compute services. I'm picking up some ones that we are using heavily. So compute engine is basically equal to EC2 in AWS. This is the service where we can get VMs very easily. So key features are starting running the pre-built and pre-configured VMs quickly. Those VMs could be distributed in anywhere globally in the world, and you can configure how many virtual CPUs or GPUs and memories it contains for that VM, and also encryption as by default added into all the VMs if you click one to process your data. And after this, the other one we are using heavily is Kubernetes engine. Yeah, Google has a fully managed Kubernetes engine called GKE. We built our data platform on top of GKE to make it be able to auto scale to echo our first presentation about IBM Cloud and virtualization and containerization. This is the Google service supporting containerization, and the horizontal pod auto scaling features is built pretty well, and we are leveraging the services to keep our cost low. And also, this is enterprise ready. We have put our data platform on the Kubernetes engine in production to handle all the data that we generated. Last but not least, as the cloud function. So this cloud function is a scalable function as a service. Same thing as AWS Lambda. Be able to run your code with zero server management. It also could be easily connected to other Google Cloud services like storage service or data processing services to get the data processed and also persist into storage if you want to permanently keep them. Yeah, with that being said, we can jump to the storage and database services that Google provides. First thing comes to us as to the Cloud SQL. This is a fully managed relational databases. You can choose either to use MySQL, Postgres, or SQL Server. There's nothing too different, but it's a fully managed. You don't need to create those databases by yourself. Basically, we can get the database instance in like 1 or 2 minutes. And security is also being managed by Google. With that, Google also provides another database service called Cloud Spanner. It's also a fully managed relational database. The major difference between Cloud Spanner and Cloud SQL is it's a strong consistency and be able to 99.999% available. We also use Cloud Spanner to keep the data that we want to use globally, and it can be easily scaled globally to make the latency and the availability pretty high. After this, I'd like to jump to the new service called Cloud Bigtable. Again, this is a fully managed, scalable non-SQL database for large analytics and low latency persistence. To echo a question in our channel, this is a time series optimized database with very low latency. And could scale up and down according to our volume and flexible automated replications to optimize the workload too. Last but not least, we'd like to bring cloud storage on the table, something similar to AWS S3. It's a fully managed object storage for any amount of data. You can keep your files into cloud storage very easily. And also it has different tiers of storage with different cost rate. We are using the cloud storage to persist our data in long term. So with that being said, I'd like to jump to the services related to big data and machine learning. The first thing comes to us, which is heavily used in Geotab, is BigQuery. This is a serverless, high scalable and cost-efficient multi-cloud data warehouse designed for business agilities. And it has four main key features that we were using every single day in Geotab data and analytics department. The first one is we could use it as a query engine. It will support full SQL statement queries with petabytes data being analyzed for every single query. And the second one is it could be used as a machine learning engine. So BigQuery might be one of the earliest query engine which support SQL statement plus machine learning models in SQL statement. So it's very easy for us to write some POC or MVP machine learning models into our SQL statements and get the result in seconds. The third thing is Google BigQuery has very good support of GIS. So in a use case as Geotab, we connect all the vehicles and would like to collect the GPS data. So this GIS support is very useful for us. And last but not least, Google BigQuery could connect to the sheets like Google Sheets. So we can, if we have data in Google Sheets and would like to get it analyzed by a SQL engine, you can get them connected in seconds and start to write your SQLs on top of that. And also, BigQuery is used as our data warehouse for all the structured data. So we have several TB data ingested into BigQuery and tons of models were running on top of that. So following that, I'd like to introduce PubSub, which is messaging and ingestion for event-driven systems. And we could also do streaming analytics on top of that. Something similar to AWS Kinesis. It could be auto-scale, ingest global messages, routing to simplified multi-region systems, and also could support quite a few SDKs like Java, Python, and SQL. We do use PubSub to do the message ingestion, and also this is a place for us to keep some event-driven messaging systems. And next one is data flow. Usually we use data flow together with PubSub. So PubSub will be used as a message queue, and data flow will be used as the processing systems. The highlight features of data flow would be it's fully managed. It could be horizontally scale up and down, and also they support Apache Beam jobs as Spark or Flink. So if you have Apache jobs already created and you are using Apache Spark or Apache Flink to run those jobs, it could be easily migrated to Dataflow to do the same thing on top of a fully managed service. And right after that, there's one more thing we'd like to bring on the table as AI platform. So this platform is more data scientist oriented. You could deploy, manage, and train your models on top of that, consuming all the data that was persisted in BigQuery, Google Cloud Storage, Bigtable, all the database services that we have mentioned before. And this could like support end-to-end ML lifecycles and ML ops, a very powerful platform to make your data scientist happy. Yeah. So with that being said, that's all the services that Geotab were using heavily day to day to support our customer and processing and persisting all the data that we have. It's not covering all the services that we are using, but just highlighting some of the services that we were using heavily and could be easily matched to CCS scenarios. Thanks.
Yeah, and to wrap this up, I want to thank everyone here for your time. I wanted to emphasize that our presentation, the objective of the presentation was the introduction of Google Cloud services, and we will be linking the mapping table between the AWS, IBM, and Google Cloud and the CCS architecture in the slide deck. If you have it, for easy reference in the future. If you have any questions about the material that's been presented today, Nate and I will be around for Q&A. Also, sorry, one more slide. On screen, there's our contact information if you have any questions or queries that come up at a later date. Thank you.
Thanks.
Okay, thank you very much. I responded to Ravi's question, but by mistake I put it as a private chat. So let me put that on the public chat as we wrap up here. And I gave a general question for the CCS project, but of course, Geotab as a company is very familiar with aftermarket devices, and I'm sure you can get more information from Geotab as you getting involved in the various projects we have. Thank you very much, Kevin and Nate, for this presentation. Let me check if there are, yeah.
Thank you so much for having us.
Okay, so that's the end of our presentation today. I will end by just putting on screen the working diagram that I think many of you have seen before, but this is a schematic view of kind of architecture we are most often exploring in CCS. And so all of what you have heard today has been about how we may apply this on various cloud solutions and what that would mean and what the choices and trade-offs may be for choosing these technologies. Are there any final questions today? Otherwise, we will wrap up this session. Welcome to join us in all of the other sessions this week for CVII, Android SIG, and others. For CCS specifically for CCS, we have another session on Friday where we will have a demonstration of some of the software shown in this picture, running software, and demonstration and deeper explanation of that software. And we may have then also a little bit more time for discussion and Q&A. Thanks so much for joining us today.
Thank you.
And we will wrap up the session there. Hope to speak to you soon again.
Thanks, bye-bye.